In 1895, a 16-year-old boy imagined himself chasing a beam of light. This thought eventually changed the world forever. The boy name was Sir Albert Einstein. So, what was really that thought, and how could one thought change the whole world? But to understand Einstein, we need to understand Sir Isaac Newton's three laws of motion and the law of gravity. According to the law of gravity, every object in the universe enacts its own force of attraction on another object. And this force is the reason why we are stuck on Earth and why the moon orbits the Earth. But Newton's laws of motion didn't answer like what is the source of gravity, why do objects attract each other. This remained a mystery until in 1915 Albert Einstein proposed his general theory of relativity, or in other words, the theory of gravity. Before that, in 1905, Einstein published his theory of special relativity. It deals with speed of light and motion of objects. It was fine with non-accelerating objects, but the theory doesn't apply to accelerating objects or objects falling under gravity. This remained a mystery until on one fine day, Einstein was observing a window washer on a ladder and thought about what he would be experiencing if he will be falling. He imagined himself falling, so he would be in a free fall under gravity at 9.8 meter per second square, and on the surface of the earth you would weigh whatever you weigh. But imagine if you are in a spacecraft moving in upward direction with the same acceleration 9.8 meter per second square as here on the ground. In both the cases you weigh the same as you do on earth. So Einstein realized that the observer would not be able to tell if the person is on the surface of the earth or in space. That's because they would be moving exactly at the same rate of acceleration. This phenomenon is called as the Equivalence Principle, which states that an object that is accelerating free of any gravitational pull is essentially no different than the same object that is stationary but affected by gravity. In other words, something moving in space with no gravity has the same mass as something on Earth that is not moving. Now, Einstein unified his special theory of relativity and theory of gravity. To further understand, Einstein started to experiment with the beam of light. He imagined what would happen if he pointed a laser beam from one side of the room towards the other. If the room were in the spaceship that was moving upwards with the same acceleration rate as Earth, the height of the beam would slightly be lower on the other side of the room. As the spaceship moves up, it curves the light and causes the light to bend down. But Einstein applied this principle in space. When he thought about the same experiment on Earth, then light would appear straight, and Einstein wasn't convinced, as this violates the principle of equivalence. Because the acceleration on space and gravity on Earth is same as 9.8 meter per second square, therefore the beam of light should travel same in both the cases. Now Einstein realized that the only possibility could be that the light beam must be bending under the influence of gravity and acceleration. So what does bending of light mean? To answer this, he came with a brilliant hypothesis that light might be following shortest and straight path it could. But in space, there is no straight path. Therefore, there may be an inherent curvature. And this idea revolutionized the subject of space, that space somehow gets curved in the presence of gravity and creates an illusion that light beam is being curved. He hypothesized that whenever matter or energy present in space, it creates a curvature. To understand this, imagine a trampoline with two types of masses, a heavy metal and a piece of marble. When the metal is placed on the trampoline, it bends the trampoline. When the piece of marble rolled on the surface, it orbits the heavy chunk of metal. In this scenario, we can see that no force is acting on the piece of marble, but it is still revolving around the heavy metal. Einstein said that the same thing happens in the universe when sun acts like a chunk of metal and creates a curvature in space. The same thing happens to all the objects in the universe. So according to Einstein, matter and energy warps, bends space and time, making nearly objects fall towards it. This remarkable theory not just talks about the three dimensions of space but also time. That's why the term space and time. But how does the time come into play? And this is where Einstein used his theory of special relativity to explain about time. The speed of light is same for observer in any frame of reference. Either the object is moving or in any state of rest. Imagine a light beam traveling from point A to B and place a massive object like sun between these 2 points. The sun will curve the path and the distance from point A to B will increases. So it will take more time for light to move from A to B than in the absence of sun. But this concept violates the theory of special relativity, which states that the speed of light is independent of the frame of reference. This means that regardless of whether the light beam is traveling freely or under the gravitational field, it must take same time for it to travel between any points. Therefore, for special relativity to be valid, time must slow down. In other words, time moves slowly when you are in space and moves faster on Earth. This phenomenon is called as gravitational time dilation. But no one took Einstein very seriously until astronomer Sir Arthur Eddington performed an experiment on general relativity. He found that sun would warp space around it and caused the light beam to bend and change in the position of the star behind the sun. Eddington experiment proved that Einstein was indeed right, and this made Sir Albert Einstein popular worldwide overnight. Today we have enough evidence to prove Einstein theorems, and this created a new window to look into the universe.
Relativity, that mass and energy are both but different manifestations of the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is put equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Cockcroft and Walton in 1932 experimentally.